so let me know. And we're going to talk about data visualization. So first introduction, what is data visualization? I'm sure most of you know, but data visualization is the set of techniques that we use to represent data in a visual manner. Hey, I know you. Okay. By definition, data is like the left side of the brain, right? It's called, is analytical, it doesn't have that much soul, right? When we use data visualization, we let the right side of our brain, which is the most creative part, the artistic part, we let it like take some control in how we play with data. So overview, we're gonna talk about the main goals of data visualization. We're gonna talk about the basic types of charts that exist. Most of them you'll probably know. And at the end, I'm gonna mention some plugin libraries in case, just so you're aware that they exist. Like anything with Python, we're gonna teach in this course, in this bootcamp, like the core libraries, but there are probably like thousands of libraries that we're gonna talk that are probably useful one way or another. So about goals of data visualization. Data visualization serves three main purposes. The first one is to communicate an idea. Here the goal is we wanna communicate something to someone else, to a third party that might be a technical person or might not. In this case, data visualization is one of the most useful and impactful techniques that we can use for this. This is an example. This chart on the left is one of the earliest uses in history of data visualization. In 1854, in London, there was an outbreak of cholera, okay, like a disease that was killing lots of people. At that time, the doctors believed that the cholera was spread through air. There was this theory, like back in the 19th century, of the miasmas, which was something like there were some bad gases in the air that were making people sick. Okay. There was a doctor called Jon Snow, like the Game of Thrones guy. It's not the same, like it has an age, like Jon, right? But similar name. And he thought otherwise. He thought, oh, I think the vector of contagion of how this disease is spread is through water, not through air. So what he did is he went to the center of London, to the area where the most cholera cases had been detected. And then he went house after house, and this is a map of that area, house after house, and then for every person that got infected, he drew a little rectangle. So here we have like a zoom version. Every one of those rectangles is a person that got sick. And he found, like at the very center of the disease, of the outbreak, he found this, in Broad Street, a pump of water, and that was right in the center. So that water pump was used by all the neighbors in that area. So what he did is he plotted this map, he went to the city council, and he managed to get that pump closed, like they closed it. And soon after, the cholera outbreak stopped. It turned out, like back in the day, the sanitation, like the pipes in the streets weren't that so great. So some of them had holes. So what was happening was like houses sewage, like garbage stuff was mixing with the drinking water. So that was actually the reason why they were getting infected. So in this case, thanks to this map, thanks to this data visualization, they actually stopped the disease. That's the main goal. That's what you will probably use the most, the main reason you will use data visualization. There's another one, which is data understanding. In this case, the target audience is ourselves. We can use data visualization to gain an understanding of our own data. Like we can use it, it's very effective to find patterns in data. When you're looking at numbers, it's hard to actually analyze them and find what's going on just by using numbers themselves. So we usually use data visualization to help ourselves. Next classic example of this, of data understanding, is this data set. It's called the Anscombe's Quartet. It was created by a French dude, François Anscombe, I think. And this is how the data set looks. Okay, it has just 4 series, 1, 2, 3, and 4. Each one has 2 variables, 3 independent variables, X and Y. And they have numbers. So let's say you're an analyst and you download this data set, someone gives it to you, and then you say, okay, for each one of those 4 series, I'm gonna calculate some statistics to gain an understanding of how they look like. So what you would think is like, hey, this guy, whoever gave me this data, gave me 4 times the same data. Why? Because each one of these 4 series has the same mean of X, the mean of Y, the same variance for each one, the same correlation, etc. So from a data standpoint, they look exactly the same. However, the moment you plot them, you see that each one of those 4 series looks completely different. So this is something that if you just check the numbers, it's very hard to figure out. But the moment you visualize it, it's obvious that they are different. The third goal of data visualization is monitorization. We can use data visualization to monitor how processes and how target KPIs evolve in a company. This is usually done through the use of dashboards. Dashboards are just visual interfaces, usually a website where you display key metrics that are relevant to your company, to a specific team, to a specific person. Okay, this is a real example of this data set, and if you click, there's like an article that talks about a guy that he was the first data person at a company called 500px, and when he went there, like he realized that every week the analyst was sending a report to the CFO and to the CEO, and this was how it looked like. What was happening? Like no one was actually paying any attention to this because this is insane. If you're asking your CEO on a weekly basis to go through this crazy stuff, right? Like he might not even be a technical person, he or she, right? Like they might not even know Excel. You are asking them to actually do the job of crunching everything just even before getting to the insights. That doesn't make sense. So the first thing he did is he turned this into a very beautiful dashboard. What that meant is all the job of data cleaning, data aggregation, etc. He did it for them. So that way, like the CFO, CEO could only focus on what really mattered, finding insights and making better business decisions. Okay, that's like, if you are the first data guy in a company, this is like the fastest ways you can add a lot of value. It's not machine learning, but it's super helpful. Like going from here, I have a Google Sheet where I post a bunch of columns. No one really uses that to this, okay? Now we're gonna talk about basic types of charts. And this is a choose your own adventure diagram. You're supposed to start in the center. Oh, what would you like to show? A relationship, a comparison, etc. And these are all different kinds of standard charts. Okay, we're gonna see some of them. There is like I said before, the data visualization is probably the most artistic and creative part of data science. So that means that probably you will feel the urge of creating your own super cool new data visualization, here and there. And that's great, okay? However, I would always advocate for the use of standard charts, like charts that have a name that you are not creating on your own. Why? For two reasons. First reason is, if you show someone and you're trying to communicate an idea, if you show them a standard chart, they already know how to interpret a chart, right? Like I'm sure you've seen like some websites where you see a cool data visualization and they actually have to explain how to interpret it. If you have to explain how to interpret a chart, probably it's not a good chart, okay? Like it should be obvious, okay? The second reason is, if you are using a standard chart, probably whatever coding library you use has an easy function to plot a chart. If you wanna make the charts on your own from scratch, like picking the points and everything, you're gonna have to build it on your own, okay? That being said, sometimes it's super useful to create your own because you have a very specific need. Of course, like we said, it's an artistic part of data science, so feel free to do so. Once you do that, once you go crazy, like creative with your visualizations, you need to be aware of what is called chart junk. We call chart junk, and I think that term was defined by Tufte, Edward Tufte, I think. Maybe not, I think so. He's like one of the parents of data visualization. Chart junk is all the stuff, all the visual encodings, all the information that you add to a chart that doesn't add any informational value, okay? This happens a lot when you talk to like analysts and stuff and they go to, oh, let's make this chart 3D. Why? Because it looks cooler, okay, things like that. So we have an example here. This is like an infograph and it's insanely complicated to read. Why? Because they decided to use a tessellated pattern. And if you see this, like with those black and white checker pattern, it's very hard to know the differences. Like, why are you adding that? That's not helping. Right? That's not telling you information. It's just making it way more complicated. And then you have this one, which is insane in many ways. Like one of them, like they chose 3D charts for some reason. Everything has like no value at all, the y-axis. Just in data visualization, simpler is better. Right? Try to do, if you think that one chart is too overloaded, do 2 charts. Okay, don't focus on, oh no, can I display 5 different variables in one chart? Do 2 charts or 3. That's okay. Like no one is charging you by the charts, so Okay, about basic charts. Scatter plot, the most common one. We use scatter plots usually when we want to explain the relationship between 2 numerical variables. Okay, 2 numerical variables. Okay, this is actually one of the first uses of a scatter plot. It was done by Francis Galton, who is the cousin, Charles Darwin's cousin. So he did in 19th century. He analyzed 903 families, and he plotted the average height of the kids versus the average height of the parents. And here we have like a more modern version of that chart. So what he saw is for kids whose parents were very short, the kids were taller than the parents. And for kids whose parents were very tall, the kids were shorter than the parents. So in this black line would be like the perfect relationship between parents and kids' heights. It was a little bit slanted. So he saw that the kids' heights tended to go back to the mean, to the overall population mean. Their heights tended to regress to the mean. That's the origin of the constant regression, like that actual chart, that analysis that guy did. Line charts. We use line charts when we're trying to display the evolution of one numerical variable versus another. Usually time. Usually one of them, the x-axis is time, okay? But you can call them trend lines also in that case. Very simple. So here we're displaying the population in 3 continents. One hot topic regarding line charts is the set of the y-axis, okay? Like I'm sure like you've read something about data science, you've seen like, oh, this chart, the y-axis is not set to 0. It's very misleading. And sometimes it's true. We have this example, this is from Fox News, and they were showing the evolution of the cost of gasoline, of gas, in the US, like last year, which was the year before Obama, and last week, which was the first year that Obama was in office. If you look at this chart, it sounds like the price of the gas actually doubled because, you know, before it was like this, and now it's twice that size. In reality, it's not, right? Like if you see this chart, the axis, it's said to see the lowest value is 2.90, right? So it spoke like the spike was like 40 cents in a year. So they were using that y-axis to actually mislead and increase and make it like a more dramatic spike, when in reality it wasn't that much of a spike price. That doesn't mean that you should always follow blindly the set to the y-axis to 0. And this is controversial. Like maybe someone else will tell you, always set it to 0, okay? And that's a good practice, but sometimes it's not. For example, here on the bottom left, you have like the world record for 100-meter running over the years, right? So for men, I think. So if you see that, it looks like, oh, we haven't actually improved at all, right? Like, you know, it's almost horizontal. Well, that's just because the overall scale, right, is like very big. It's like goes from like 10 seconds to 11 seconds, right? So you have like 90% of the chart is not even reachable. That's why it looks like a flat line. You show like a shorter y-axis, it looks like in reality, like the record is being like demolished every single year. And now we're actually being faster and faster, right? Like in recent years. So again, if you don't know what to do, set it to 0, but sometimes it's good to break this rule. Bar and column charts. Column charts are usually called bar charts, and horizontal charts are called horizontal bars. Like the technical term is column and bar charts. Everyone calls them bar charts. When do we use horizontal bar charts? We use them when we want to compare discrete quantities of a variable that is categorical. That means a variable that it doesn't have any kind of natural order. For example, here we're displaying the number of Twitter followers by NHL team, like National Hockey League in the US. So there is not like a natural ranking for the hockey teams. So you guys use a horizontal, right? You are not telling them, oh, this one is better than this one. There's no natural order. Here on the right, we're showing like an ordinal variable. That means a variable that is not a number, but it has some order, like it's the year. We're showing a population of dolphins and whales by year. So it makes sense to use column charts, vertical bars. Histograms, super useful when you want to find the distribution of one numerical variable. How is the data distributed, okay? Here we're showing the 2013 NHL player height. So basically you take like all the players that played in the league in 2013, you measure the height in inches because it's a US chart. Don't use inches in the real world, please. And it's very cool because it gives you a lot of information, like, okay, who was the shortest player? Okay, you see this guy, that was like 66 inches. Who was the tallest player? How tall was the tallest player? Okay, like 79 inches. Was like the most common height? Okay, it's either 71 or 75. Okay, so it gives you a lot of information about one single numerical variable. If you want to compare a numerical variable, how it's distributed among groups, you can use a box plot, also called a box and whisker plot. It's probably the most complicated standard chart that exists, I'd say, but it provides a lot of information. Here, for example, we're comparing on the left the weight of automobiles that are manufactured by the region. Okay, so we can see just at a glance that US cars tend to be like bigger than Asian cars. Okay, that's something like you see like the boxes, and this one's a little bigger. So it provides like a lot of information. Okay, If you have like more than 5 values for the variable that you're comparing across, don't do that because then it gets like very convoluted. Okay, that's just an advice. How do you read these boxes? Okay, so this is like a description. Okay, like this is the box, and like the blue lines are the whiskers. Okay, like the box, the bottom line of the box shows the value for that numerical variable. In this case, the car weight. That is the first quartile. That is the value that is bigger than 25% of the population. Then, like the top line of the box is the third quartile. That means the value that is bigger than 75% of the population of the cars. Then you have like the horizontal line in between, which is the median. That means the car weight that is bigger than 50% of the population. Okay, and then you have the whiskers that show the minimum value and the maximum value. And then you think, hey, but in this chart on the left, there are elements that are, there are weights that are above the maximum. That's impossible. Well, like as a standard, and this is not like official, but that's common practice, you usually display the elements that are way too big or way too small aside from the actual boxes. Those are called outliers, elements that are so big or so small that are not representative of the actual data. If you included these ones on the actual box, the box would be like misleading to compare the overall population. How do you define what an outlier is in this chart? Usually you consider an outlier if it's like 1.5 times the interquartile range. The interquartile range being the difference between the first quartile and the third quartile above the maximum. So these elements are 50% bigger than the interquartile range above the maximum. And same thing with the minimum.
Sorry, about that. Well, why are
this is the most complicated.
Yeah, why are not the observations aligned in the X?
So you do that, that's called jitter. Like when you're plotting these, if you didn't have them on the x-axis, you will only see 1 point across the values. So usually you do what is called jitter. You move them a little bit just so you can see. Let's imagine you have like 1,000 points that happen to have the same weight. You will only see 1 weight. That would be kind of misleading. So you do that like a random dispersion on the x-axis, which again, the x-axis in this variable is irrelevant.
Yeah, exactly.
Just so it's visualized. Yeah, it's called jitter. And you do that like in many of these cases when you have, there are two options. Either you do jitter or you change the transparency. Like sometimes instead of that, you say, okay, instead of moving them on the x-axis, I'm gonna make them transparent. So when I have a lot of points that have the same weight, it looks darker. Does that answer your question? Cool. Other plotting libraries, Matplotlib is the one we're gonna use. It's the one that Pandas uses by default. It stands for MATLAB plotting library. That means it's a port of MATLAB plotting. That means it's horrifying. But if you search in Google like anything, how to plot something in Python, it's gonna be Matplotlib. It sucks, but that's what we have. Then you have like other versions that are more advanced. Seaborn, very cool for scientific graphs. They have like very specific, very complicated charts with just one line of code. Bokeh, it's pretty awesome. It's part of Anaconda Continuum Analytics, the creators and maintainers of Anaconda. It can handle like millions of points with like in a breeze. So it's very cool. ggpy is a port of ggplot for those of you that like art. So it's similar. Alter, created by Jake van der Plas, an awesome guy and maintainer of many packages. It's very, very nice. And I wanted to add Plotly. I'll share it later in Slack. Like there's another library that's been pretty popular called Plotly and Plotly Express. I can share that later in Slack. Okay, recap. Okay, so we talked about the main goals of data visualization. Then we talked about different kinds of standard charts. In reality, like I use all of these like 99% of the time. Okay, sometimes when you want to daze an external party to communicate an idea, you can go crazy and do something else. When I need to find some very interesting insight, I go crazy and find something else. But 99% of the time, scatter plots, bar charts, histograms, line charts will do the job. Okay, we talk about chart junk. Like I said, don't go crazy, don't go overboard. That's not helping anyone. Okay, it's not helping your audience, it's not helping you because you're gonna have to explain your chart to everyone else. And then we mentioned different plotting libraries in case you hate Matplotlib, which you might, or you wanna do like something crazier, like more advanced. Got it. Okay, so awesome. Let's plot some cool stuff. Cool.